So about those absolute values, when we take even roots of even powers, this is one of these things in math that 90% of the time or so, it doesn't really matter. And then you get into the habit of ignoring it. And then one time it really matters, and it's really, really bad. How bad? I had a friend who had to rewrite about 50 pages of her PhD thesis because she ignored the absolute value when you take an even root of an even power. And that was one of the times when it's really important. So when can we ignore the absolute value? Of course, we can ignore it if we're only interested in positive values of the variable to begin with. We can also ignore it if we're taking an even power at the end anyway. And so whatever we have is going to turn out to be positive. We can ignore it if the remaining root, whatever's left, is only defined when the variable is positive. So as long as we're restricted to the real numbers, that's going to happen fairly frequently. However, it is very important to include the absolute value first and then decide whether it can be ignored. As far as this course is concerned, it is never wrong to include the absolute value in an expression where you took an even root of an even power. Your work should always show that you had the absolute value and then decided to drop it when you've taken an even root of an even power. And as far as this class is concerned, you never need to decide to drop it. But let's see a couple of examples to consider where we can drop it and where we can't. So we've got a square root of x to the 8th. Right, that's a square root of x to the 4th squared. Square root and the squared cancel, provided we take the absolute value. But now that x to the 4th is an even power of the variable. So x to the 4th is going to be positive anyway. So we don't need to include the absolute value there. In this next example, we have the 4th root of x to the 7th. Right, so that'll be the 4th root of 7 is 4 plus 3. So x to the 4th times x to the 3rd. 4th root x to the 4th times 4th root x to the 3rd. 4th root and 4th power cancel out. We have absolute value of x times the 4th root x to the 3rd. But now, 4th root x to the 3rd, we notice that x to the 3rd is going to be a negative number when x is negative. So if x is a negative number, 4th root x to the 3rd is undefined. So if x is a negative number, the whole expression is undefined. Everywhere it's defined, the absolute value of x is just the same as x. So we can drop the absolute value there. In this next example, we have the 4th root of x to the 6th. So 6 is 4 plus 2. So we have the 4th root of x to the 4th times x squared. So 4th root x to the 4th, 4th root x squared. Cancel the 4th power and the 4th root. And we have absolute value of x times the 4th root x squared. Okay, let's see. That's an odd power of x. So if x is negative, without the absolute value, that would be negative. So we need the absolute value there. But can x be negative? Well, what's inside the root is an x squared. So even if x is negative, we're taking the fourth root of something positive. So we do need the absolute value here. Last example, we have the square root of x to the 10th. 10 is 2 times 5, so this is x to the 5th squared. Square root and square cancel out, and we have the absolute value of x to the 5th. And again, this is an odd power, so if x is negative, that would become negative without the absolute value. And there's no remaining radical, so there are no concerns with this being well defined. We do need the absolute value here as well. Okay, so if you can sometimes drop the absolute value for an even root of an even power, but not always, does that mean whenever you've simplified a radical, you should just throw an absolute value in just to be safe? Well, no. Why not? Because when we take an odd root of an odd power, that does not give rise to an absolute value. So for example, if we simplify the third root of 27x to the fourth, that is equal to 3x times the third root of x. And it is not equal to 3 times the absolute value of x times the third root of x. To demonstrate that, we're going to plug in x equals negative 8 and show that these two give us the same result, and that last one gives us a different result. Now, the hardest part of this whole process is going to be working out 27 times negative 8 to the fourth power. We'll use a calculator for that. This is the third root of 110,592. Fortunately, we can use a calculator to take the third root of that number as well. And we get the much nicer number, 48. Okay, so far so good. If we take 3 times negative 8 times the cube root of negative 8, well, that'll be 3 times negative 8 times negative 2. 3 times negative 8 is negative 24. Negative 24 times negative 2 is positive 48. So we see that indeed those two are equal. On the other hand, if we take 3 times the absolute value negative 8 times the third root of negative 8, well, that'll be 3 times positive 8 times negative 2. So that's 24 times negative 2 is negative 48. We cannot just throw that absolute value in there. We have to know which circumstances require it, namely, when we took an even root of an even power. Often in reality, when we're simplifying radicals, though, we're actually only interested in the positive real numbers to begin with. So often, when we're just trying to practice our simplifying moves, we'll have an instruction that says something like this. Assume all variables represent positive real numbers. So that means everything's positive to begin with. You don't have to worry about whether or not there need to be absolute values here. So if we assume all variables represent positive real numbers, and we want to simplify the square root of 3 times x to the fourth times y to the seventh, well, we'll have 3. That doesn't have any factors at all, so we'll just leave that as 3. X to the fourth, that's x to the 2 times 2. Y to the seventh, that's y to the 3 times 2. then multiplied by y to the 1. Now I'm going to take just the parts that are perfect squares, and I'll have the square root of x squared squared, the square root of y to the 3rd squared, and then the parts that are not perfect squares, I'll leave inside the radical. So I'll have square root of 3y. The square root and the square cancel out. And because I'm assuming that x and y are positive numbers, I don't need an absolute value here. X squared y to the 3rd square root 3y. Because I'm assuming that all of my variables, x and y in this case, represent positive real numbers, I don't need to worry about whether or not I need to take the absolute value of any of them.